Hi, everyone. So that we are on page 128 right now. On the very top part, I was supposed to go over this last lesson, but some classes I didn't. So we're gonna just go for that. And even if we did, just go over it again. It'll help us with what we're doing today. So if you remember, we had the equation y is equal to b to the x power, and we can change that to log base b of y is equal to x, right? Same thing, right? They are equivalent. And there are some restrictions. So if you remember, so I'm gonna just write this a little bit bigger here. So y is equal to b to the x power. And so for x, does x have any restrictions? Can x be negative numbers, positive numbers, 0? Yeah, x could be all those, right? So it doesn't matter, there are no restrictions for x in this case, for the exponentials. So we're gonna say no restrictions. So what in the world does that mean? Oops, no restrictions. And explanation, x can be. So x can be any, again, real, as opposed to imaginary number. So any real number, positive, negative, a fraction, decimal, all that kind of stuff, right? And so what about b? What can b be? What can b be? All right. So remember, this is the base. Now, if you remember a couple lessons ago, right, we talked about what if it was negative, right? Remember, we saw the graph, what happens when it's negative, and did that little like dot thing, right? Yeah, it can't be negative. So b, and then what about if it was 1? Like, yeah, it can be 1 because it wouldn't be exponential, just like flat line, right? It was just like 1 times 1 times 1 times 1. It's just 1, right? And nothing is changing. It's not growing or decreasing. Yeah, can't have that. So b has to be bigger than 1, right? So that's the explanation, is bigger than, greater than 1. All right. It could be 1.1. It just can't be 1 as long as it's increasing. Oh, can it be decreasing? Can it be a fraction? Yeah, right. Well, what kind of fraction? Like 0.5? So yeah, it could be 0.5. So let's amend this. Did you guys notice that? Were you like, wait, Miss Lee, I thought it could be like 0.5. So there we go. So for the class that we, fix the thing. So it can be greater than 0, right? B can't be 0 because with 0, it's just 0, and that's not fun, right? But so B is going to be greater than 0, except we had to put an exception here. B cannot equal 1. Okay, that's the only exception for that. So we'll say B can be, lowercase b, keep that same. So if this is a lowercase, this has got to be a lowercase. So B can be any positive number, except what? Except, now it's except, not accept, right? We're not accepting the award, right? It's except 1. All right, now what about y? What can y be? So y can be, so this whole thing, if it's always going to be positive, right? So this is, remember, the basic, very pared down exponential equation. Okay, so then b can be anything. Remember, it just can't be 0 because b can't be 0. So therefore y can't be 0, because the only way we're going to get 0 by multiplying is if one of the numbers is 0. And if the only number we're multiplying by is not 0, it's never going to be 0. So it's going to be anything greater than 0. So y is greater than 0. So y is, or y can be, I should say can be, any positive number. I should just say any positive number, period. That's it. Can't be negative. All right. So now, now that we went through the restrictions, so those were it. Now we're going to go on to the next part right here. Yes, on page 129. All right. Told you we're going to talk more about graphs. So here it is. And if at any point you're like, oh wait, she's writing way too fast, please pause. Is it here? There? I don't remember. All right. So here we go. So I love how this says the obvious. It says a logarithmic function is a function involving a logarithm, right? Yeah, duh. Okay, so what does that look like? Now, remember we saw this yesterday in the last lesson, right? This is our exponential right here. Here they use b, but I'm gonna make it a little more concrete and we're gonna say b is 3, okay? Because the other example was where b was 2, right? If you look over here, I'm gonna scroll a little bit. Yeah, right here. So this is, remember, 2 to the x. So we have already one for 2 to the x. So we're just going to do one for 3 to the x. Okay, so we'll just try it out. So sorry for all the scrolling going on. So here we go. We're going to actually make this table. And if you notice here, they give you the x's, right? We got -2, -1, 0, 1, 2, and that's it. So here we go. So we're going to go -2. So on the left-hand side of your paper, you're writing -2, -1, 0, 1, and 2. And then we're going to fill this out. How are we going to fill it out? We're just going to plug in those numbers. So I'm going to actually change my color to purple because this is all purple. Okay, so h of -2 is equal to 3 to the -2 power. Now, if you remember our negative exponents, right? What does that mean? Please do not say it makes it a -9, right? That's not what that means. Right? Go back to your rules again. Remember that negative exponent meant that it was the denominator of the fraction, right? It goes to the bottom, right? So it's just going to be 1 over 3 squared, which we know to be just 1 over 9. All right. So this 1/9 is going to go right here. All right. And I'm going to give you a little bit of time. I want you to do the exactly same thing, except it's going to be, with -1, 0, 1, and 2. All right. So I want you to pause right now. Do it, and then share your answers in the chat. All right. Either to the teacher or to, not me, obviously, or to everyone, right? So that you guys can check your answers, right? And then press pause, press start. All right. You got it? All right, so hopefully that didn't take too long. But here's the work here for the rest of them. You should be able to check these. These should be the same. If not, then just let the teacher know. Notice right here that this is 3 to the -1, which is, remember, 1 over 3. And again, check your 3 to the 0. Did you put in 0 or did you put in 1? Hopefully you put in 1, because anything to the 0 power is what? 1. All right, and so these are the numbers that you should have gotten. Please check that. And what we're going to do is, so that's literally what we have here. We're just going to pretend that instead of the b squared is going to be these numbers. All right. So now the question is, how do we do the inverse? Just like that, right? Remember Freaky Friday? We talked about that, right? So we're taking the x and the y, and we're can't completely do that because it doesn't work like that. So literally that's what we're going to do. So we don't have to do this work right here because, I mean, we can, but we don't need to because we already have the table, and we're just gonna literally flip them. So here, so instead of being -2, 1/9 is gonna be 1/9 and then -2. So I'm gonna just graph this. So what was that? What is that gonna look like? So x is 1/9. So it's like right about guesstimate, right? So do you see the distance right there? It's like very, very tiny, right? So very, very tiny to -2. Yeah, -2. I'm like, is that -2? So this is about -2 right here. So about that same distance, about right there, there's -2. That's going to be like right about there. Okay, that looks like a heart at this point. Let me do that again. All right, so hopefully yours looks a little bit better than mine. It's like right about there. And that's going to be my 1/9 and -2. All right, barely above, or barely to the right of the y-axis. All right, and then we're going to do the next one. I'm going to just do this in different colors so we can just see all of the variety of colors. So -1/3. So this is now going to be 1/3 and -1. See, and so -1/3 is going to be a little bit more to the right. So it should not be in line with this. Should be a little bit more to the right because a little bit bigger. And here's my -1, like right about there. So we're just going to go barely to the right on that. All right. And then let's go green. All right, and the next one is 0, 1. Okay, so this is 1, 0. Okay, this is a little bit easier just because it's right on. So 1 is about this distance, so we're going to go about the same distance. No, my distances aren't the same, are they? Oh, well, it's okay. So that's going to be 1, 0. Remember how we talked about yesterday, how this had the y-intercept, and then the other one, the inverse, had the x-intercept and not the y-intercept? Remember, that's the y, that's now the x-intercept. What used to be the y-intercept, flipped. All right. And then we got 1, 3. Instead of 1, 3, we're going to put in 3, 1. And here we go. So the 3, so 1, 2, 3, have them be about the same distances, right? And then 1. So we know this is 1 right here. So we're going to just match that up. Do you see the curve that's like forming? Do you see it? And we're almost there. So this is 2, 9. So this would be 9, 2. So here, 4, 5, 6, 7, 8, 9. Okay, technically that's not in the right place. Okay, that should be like way the heck up here, but just saying, okay. Just saying. Oh, I should have lined that up too, because notice this didn't line up as well. Bad math teacher, I'm sorry. But you see what I'm saying, okay, you get the picture. These were just B's, okay? I'm just trying to like get it a little more concrete here. Okay, so that's going to be our 9, 2, so it's like right about here. All right, and if you see our graph, we're just going to, remember asymptote was right there at the y-axis. It is not going to cross that because this 3 to the x will never, no, not never. I mean, the inverse of 3 to the x, the inverse of that is never going to get 0, going to equal 0, can't. So we're just going to go, so make sure you're not crossing it. And we're just going to go, oh, shoot, that's terrible. I'm going to start from over here then. Maybe I'll get better result. Okay, kind of like that. All right. Pretend that I went through all the points. Okay, so, but that's what our log is going to look like, just like that. You just literally take your exponent, the 3 to the x, and then you find out what those are, and then you just switch them. Your log graph right there, done. Okay. So I like to just think about it like exponentials, and then I just flip them just because it's easier, because I don't want to think about logs. Logs are complicated. But so that's how you graph an inverse. So hopefully that's a little more concrete. All right. If you were going to use like just 1 over b, then obviously the inverse would be just 1 over b, and then the y would be -1. Right? How do you graph that? It's a little more abstract. So we'll go with that. So write the equation for the inverse of h of x is equal to b to the x power. Okay, we can do this. So remember, I'm just going to change this to y, just like how we normally would for inverses. Remember how we did inverses. Y is equal to b to the x power, right? And then what do? Freaky Friday, right? X is now the y and y is now the x. There we go. Now what you do from here is you're just going to change it to log form. All right. So I want you to pause the video here and then try to change it to log form. 30 seconds-ish. Go. All right. So I'm assuming that you have tried this out, and let's try it. So remember, the log is going to be, let's see if we can do this. So it's log base b of what? X is equal to y. So now if you were the one who was doing the E thing, remember the E thing, the loop-de-loop, you wouldn't have been able to have done it this way. You would have had to change it. So make sure you rewrite to b to the y is equal to x, and then you can do your loop-de-loop. So, or your L, I should say your L, right? So log base b of x is equal to y. Okay, that's what you would have had done. If you try to do it here, it would have messed you up. You would be like log base x. But if you remember the do now from yesterday, you would remember that. Remember the exponent is what is the log is equal to, because why? Logs are the exponent. And then we got the b. All right. Let's see here. So this is what you should have gotten, and we're just going to write this back into function notation. which is going to be h, so the inverse of h of x is equal to log base b of x. Happy days. Put it back into function notation. That's this. Okay, and now instead of b, we would have put in a 3 because, you know, this one was a 3. We said b was 3. That would have been this function right here. That is going to be log base 3 of x. That's what it would look like. Okay, looks like an L that fell down. All right, we're kind of and twisted. Anyways, all right. So the question is, do you think all exponential functions are invertible? Now, if you remember invertible, it's not like convertible, right? Invertible means that they are inverses. That it would be an inverse. When you reverse it, that is still a function, right? So is the inverse still a function? Is this log going to be a function? Yeah. So, and remember a long time ago, back in like lesson 1 of unit 1 or unit 4, I should say, of this quarter, like when we had a parabola and we inverted it, it was like this, right? Or maybe it was like this, there we go. And then, so it was not because it like folded over like this, right? It did not pass a horizontal line test. You remember the horizontal line test? So if you try that for the, what is it called? For the exponential, does it pass a horizontal line test? Yeah, it does, right? So yeah, it's invertible. Does it pass a horizontal line test and a vertical line test? It does both of them. It does this. Wait, ooh, can I do it? It does this. Right, try that at home. Can you do this? It's not easy. There we go. It's like, and then, so this is a little bit of history. So it would be, if you're interested in about logs and why and who made these logs up, right? There's always a reason for them. There's a purpose that serves it. So read that part. So now, when you look at your calculator, it has a log, right? Did you know that your calculator is so big that it has a log in it? Right there, log right there. You didn't even have to chop it down, but you can't burn it. So the common log, the one that you see there, is a common log. Okay, it's just, we don't even call it a common log. It's so common, we just call it a log, right? And notice right here, it just says log of x. So if you see something and it's like, oh, it's just a log of x, just like this, we assume that the base is 10. So do you remember, like we talked about a lot of invisible things, right? So in front of an x, we assume that there's a 1 there, right? But we just don't write it. We just know that 1x is equal to x, right? We also know that x to the 1 power is equal to x, right? But we just don't write x to the 1 power because it's a lot of unnecessary writing, right? And same thing with like 2 times x. We know that that's multiply, because even though there's nothing there. So instead of saying 2 times x, we just say 2x. And we assume that everybody knows that that's multiplying. And if you didn't know that, now you know. And because if we meant to say plus, we would say x or 2 plus x, right? And then the other one was, the more recent one that we learned was the square root of x. Now, if there's no number there, remember for the index, there's no number there, what number is it? Yeah, it's a 2. So instead of like saying square root like this, we just write it as square root. And we just know that that invisible number is 2. And again, if you didn't know that, now you know that, right? And then now same thing now, there's another invisible number. There's a lot of invisible numbers, right? It's not imaginary because it's real. It's just invisible because you can't see it. All right, so the log x, if we just say log x, and I don't say what the base is, we assume that it is just 10, okay? It's just 10. So log base 10 of x is just log x. This is what we're going to use most often, okay? Log x. And some calculators only have log x. They don't have like another function, another function where you can change the bases. But some calculators, like this particular one, it does. Do you see that one right there? Yeah, that means you can't. If you can't see that one, no worries. It's on there. If you have that kind of calculator, then you know it's the upper right-hand side. And then there's another one, another special one. And I told you that we kind of talked about it when we talked about Half-Life. You remember that? The game that apparently not a lot of people know. But anyways, so here, the natural log, right? We kind of talked about it, is so the log with a base of e. I remember E. It's getting back. So instead of loggy, like froggy, but loggy. No, instead of log E, we just say natural log because E is the, yeah. So remember what we said E was. E is a number. What number is it? Here, we're not going to get into that just yet. But anyways, instead of saying log base E, we just say natural log. And notice it is not NL, it's LN, even though it's log natural log, it's not log natural, right? And I think the reason why they did this so to keep the L's the same, because honestly, if it looked like this, now it looks like N1, right? And if I so natural log of X, it just looks like N1X. Yeah, that gets confusing. So I think that's why they changed it, but I don't know. I don't know about that one. So just know that natural log is ln. And on your, I know that looks like in and it's not in, it's ln, but it's just lowercase l, just FYI. All right, so there are those. Got it? Cool. We wrote it down or didn't write down. I don't know. Highlight those. All right. So the question is, okay, do you see here? So this is the log base 2 of x, which we saw yesterday, and the log base 3 of x, which we did today. Whoa. Notice that the higher the bases, what's happening to this graph? Lower. My prediction is if it was log base 4 of x, where would that be? It would be probably like even lower, right? And notice that right here, the x-intercept is the same. Just like how we noticed for the other one, remember the x and the y-intercept was always the same at 1, right? Because b to the 0 power is what? Don't say 0, say 1. Is 1. Anything to 0 power is 1, right? So this is just the reverse of that, right? Because it's the inverse. So this is 1, x is 1 when y is 0. Anyways, so where would, right here, where would log 10 be? Log base 10. Would that be above the log base 2 or below the log base 3 or somewhere in between? Those are literally your only choices. So make a prediction, write in the chat, and then we'll see. Okay. Maybe there was a pause there. Okay. So remember this is log base 10, right? And we just talked about, remember, notice that this is log base 2 and log base 3. So like that means log base 10 is like gonna be pretty like, right? So I like to just change this up to I just like changing this to the exponential form, just because it's easier for me to kind of wrap my head around it. Okay, so remember it's base 2 to the y power is equal to x, and this one is base 3 to the y power is equal to x, right? So what I'm saying here is, let's see if I can find this one, like right here, or log base 3, right? So when my x is 9, so when this is 9, my y would be 2. Do you see how that works? Okay, so that's like an actual point on here. So my y would be 3 to the 2nd power. Okay, so when my x is 9, my y is 2. All right, and so another one, a good one would be right here, right? So when x is 3, is that 3? When x is 3, what would my y have to be? It has to be 1, right? Because 3 to the 1 power is 3. Okay, so now I like to think about that with the, so I know that the log 10 is going to be down here, lower, because that's, that seems like it would, because the numbers of the bases lower. So here we go. Oh, this is c of x. So I'm just going to write this here. So this is 10 to the y power is equal to x. So I can't make this, I mean, even if y was 2, right? If y was 2, x is like 100. I can't graph that. That's like way too far, right? But so if I could do x as y is 1, right? If y is 1, so 10 to the 1 power, x is 10. I can graph that. So where my x is 10, my y would be 1. So it'd be right here. See how this goes? And we know that it's going to go through this point. So I'm just going to graph this like this. Oh, pretend it goes through there. Okay, there we go. All right, just like that. So that will be my log 10, log 10, log x. Okay, and then what about the natural log of x? What is that going to look like? where's that going to be? And this is like, remember what the natural log is. Remember the natural log of x is equal to log base what? Log base e of x, right? And what is e? Do you remember the numbers? Anybody write it in the chat? All right, remember that's 2.71828182845904523, etc., etc. Oops. Ooh, I want that. Where did I go? Okay, there it is. Oops, I went too far. It couldn't handle it. So yeah, so obviously we don't want to write all those numbers because that's really long. So it's just going to go log base e. So remember it's 2.7. So we did this one. It's very similar with just the e, and we're graphing it, right? So it's going to be in between these two, and is it going to be closer to the log base 2 or log base 3? I hope you said log base in your brain. All right, so we're going to just draw in between there. Oh, try to make it closer to the log base 3. I'm going to try my best. Still going to go through that x-intercept, right? Oops, not going to cross. Should not. Sorry, that should not cross the y-axis. Pretend it didn't cross the y-axis ever. All right, so that's going to be somewhere right in there. So this is going to be my natural log. So this is going to be my, they say n of x. N of x is equal to natural log of x. Okay, that's about where it's going to go. So natural logs, or logs in general, are always going to look like this. Okay, it's going to look like this. Exponentials look like this. Natural logs look like this. Make sense? Always like this. Kind of-ish like a radical. Kind of-ish. Okay, it's like, is it kind of like a radical? We're not going to get into that. All right, so there we go. And we're going to move on to the next ones. Okay, so now we're on this next page of 132. All right, now, apparently the Richter scale, and a lot of these numbers where we deal with like a big range of numbers, like where it's like really small numbers and really up to really big numbers, they use log a lot. Okay, that gets used often, and then we logify things, right? Okay, that's not actually a word, but we use log to kind of represent, where's my colors here? Okay, to represent these numbers. So like, for example, where's my mouse? Sorry. For example, right here, 10. So how would we write 10 as a log? Okay, so let's think about this. So 10 as a log. So 10, this is 10 to the 1 power, is equal to, let's just call it x, right? So that's going to be log base 10 of what? Of x is equal to, well, that's just going to be 10. Or just be taught log base 10 of 10. All right. This is me thinking about it out loud. So, okay, so 10 to the 1 power is equal to 10, right? So the log base 10 of 10 is equal to 1. So far, so good? So this is going to just equal log 10. Remember we told you about like the logs, like what that's going to be. So then what about, oh, that's going to be 1,000. I know you use a period here, but they actually mean a comma. Depends on what we're talking about. So that's a comma, that's 1,000. So let's think about 1,000. 1,000 is what? 10 to the 3rd power, right? Is equal to 1,000, correct? And so this can be log base 10 of what? Of 100 is equal to 3. So log 10 is equal to 1, right? So this is 1. And now this right here is log 100, which is equal to 3. Do you see how these 1 and 3, how these are much smaller numbers, right? So that's what they're doing. Okay, just saying. So that's how we can use like these very small numbers and very big numbers, because we have to go all the way to a million, right? And then they can make these into much more dealable numbers. So that's where they're getting these numbers from. Okay, that's where these numbers come from. They just logdified it. I don't remember the actual word for that, but when you use the logs, brain farting here. All right, so the Richter scale is apparently an older scale that they used to determine whether, you know, how big this earthquake is, right? They use something different now. They don't use the Richter scale. Those are still good for like just more smaller earthquakes, but the big ones that, you know, come out on the news and stuff like that, they use something else. They use this right here, the moment magnitude scale. They still use logs, but it's a lot more complex than what we're going to do right now. A lot more complex, but it still uses logs. But anyway, so the moment magnitude scale are the numbers that you'll see, and it's a lot more accurate than the Richter scale. Richter scale was like, I think in the 70s, they replaced this. But apparently not a lot of people know that. I had to do some research. So anyways, so the Earth's magnitude M is determined by using this equation. If you notice right here, you see log, right? So M, which is the magnitude, is equal to the log of what? The intensity over the IO, which is the intensity of a standard earthquake, whatever that threshold is, right? And what is very, very small. So it's like, it's the amplitude. So remember, if you remember the little thing that goes like this, and if there's a lot of shaking going on, then it'll like go, whoo, right? So it's a very tiny, small one, right? So this is 10 to the negative fourth power. What in the world is that, right? How small is 10 to the negative fourth, right? So 10 to the negative fourth, remember, is 1 over 10 to the fourth, right? Like we learned about this, and which is 1 over, well, 10 to the fourth is 1, 2, 3, 4 zeros. So that's going to be 1/10,000th. So in decimals, this is what it looks like. Just move it over to 4 decimals. 1, 2, 3, 4. That's 10 to the negative 4. I know, it's really small. So it's 0.0001 centimeter. So can you imagine how small this is? It's very tiny. So this is the number that's going to go right here for IO. Okay, and here we go. It says write an equation to model the magnitude of a standard earthquake. Well, if it's a standard earthquake, what would that look like? We just said that the standard earthquake was going to be 0.001. So it's just going to be 0.001. Oops, I left a 0 out, over 0.0001. And what is this? It's pretty much just log of 1. Okay, now let's think about this. What in the world does that mean? So we got the magnitude is equal to log 1. We're gonna change this to exponential form to help us kind of, okay, this would be the equation. I just want to know what I want you to know what it equals out to, right? So what I always like to do is change this back to exponentials, because I understand exponentials a lot better, right? So here's base 10, remember? So base 10 of what? Base 10 of my exponent, which is m, is equal to 1. Well, what is my m going to be? 10 to what power will equal 1? I hope you said 0. So my magnitude is 0. It's not very exciting. Well, you want it to be not very exciting, right? Because if it was like up at 9, if you see right here, yeah, lots of bad things are going to happen at 9. So we don't want it up there. We don't even want it at maybe even 7, right? So these are the equivalent kilograms of TNT. Okay, so let's see right here. An earthquake in California measured 6.8 on the Richter scale, while an earthquake in Japan measured 7.2. Okay, so we're going to see where it says you can use technology, but let's see if we can do this by our hands. So it says 6.8 on the Richter scale. So that's the magnitude, right? So 6.8 is equal to the log of, because it says how much more intense. Okay, we want the I, just the regular I, not the IO. So this is the I. Remember the IO is 0.0001, just like that. We want to know what the I is. How do we figure that out? Change the form, right? So we're going to just change to exponentials. What in the world is my base again? Oh yeah, remember it was 10. So because it's invisible. So that's the 10. So it's going to be 10 to the what power? The 6.8 power is equal to this. So it's going to be I over 0.001. Well, we can figure this out, right? We just use a calculator. So So here's our calculator, and we're just going to go 10 to the, okay, I guess this is technology to help us out, right? 6.8. How do you do it to the 6.8 power? Good thing we have a calculator. So it's this huge number, right? And whatever this huge number is, how do we get rid of this? Well, let me just write it down then. So it's going to be 6309, 6309, 573.445 is equal to I over 0.0001. Now, how do we get rid of that 0.0001? It's dividing. We want to get I by itself. So what do? Yeah, just like how we normally would do. We just multiply it by 0.0001 on both sides. Multiply by 0.0001. All right, and then here we go. And honestly, we can just change this, put this, oh wait, I'm just gonna do it. So multiply that by 0.0001. Make sure I have enough zeros in there. And yep, it's gonna be 630.96. So 630.96. So I is equal to 630.96, about. So I want you to do the same thing now for 7.2, for Japan, which measured at 7.2. What is that intensity difference? Okay, so try it out. Pause, try. All right, so you should have gotten something that looks like this. I didn't do the actual equation yet, or the solving part yet, but just in case if you needed it. So 7.2 is equal to log of the I over the 0.0001, right? Just like how we did for the other one. Instead of 6.8 though, we're now replacing that with 7.2. And then we're going to change it to the exponential form because that will help us figure that out. So here we go. So my base, remember, is 10. So 10 to the 7.2 power is equal to I over 0.0001, right? And just like how we did before, we're going to figure out what that is on the calculator. So it's going to be 10 to the 7.2. It's going to be this huge number. Now, remember what we did with that 0.0001? We multiplied it, right? So I'm just going to do that here. I'm going to multiply that by 0.0001. There we go. And we get, what do we get? Ooh, 1584.89. 1584.89. Got it? So I is equal to 1584.89. Yeah, that's a lot more intense, right? So it says, how many more times more intense is the Japanese earthquake than the California? So we're comparing Japanese to California, right? So this one, the second one that we did was the Japanese one, where we're going to put that on top because we're trying to figure out more, how much more intense. So 1584.89. We're going to divide that by, here it is, the Californian intensity, like this. And then we can say, oh, it's this many times more intense. Alrighty, so we're going to go right here. 1584.89. Divide that by 630.96 equals, it's about 2.5 times more intense, right? That's about 2.5. So it's about 2.5 times more intense. So even though the number, it doesn't seem that much, right? It's only like a 0.4 difference because it's logarithmic, right? Because we're talking about logs, the intensity is, it's much more strong. Okay, so times more intense. All right, there we go. So we're gonna just move on from here. And what we're gonna do is we're gonna take a look at this one more time, all right? So if you don't have time to finish this in class, make sure you go back and look at it after school, like the link, you know where the link is, right? Right there, the week at a glance. All right, so finish these ones. I would pause and do it, or if you want to just hear it and do at the same time, we can do that. So the basic exponential function, right, is going to be b to the y, I should say. Eek. So f of x is equal to b to the x power. That's our exponential, like basic one, right? The basic logarithmic one is going to be what? let's make this G. Okay, so G of X is equal to, right, log base B of X. Okay, and remember this B is the same as that B, it's the same B. All right, and the graph in general is going to look like, you make your X and Y. And remember that for logs, I'm going to make this orange, let's say. Remember, it's going to be something like this. Gets really close to that x-axis right there. Remember, the y-intercept is right here. And this one is what? In general, like for the basic form, is just 0, 1. All right. And then for the log, what does that look like? So let's go with the same one. Again, if I'm going too fast, feel free to pause me. I will not be offended. All right. And remember this one, remember instead of the y-intercept is now the x-intercept at 1, 0. So we're going to go right here. This is 1, 0. And it's going to be, oh, yeah, I can't write it that way for some reason. I'm going to draw it this way. There we go. Remember, it approaches like as y goes down, it gets really close to that 0 for x equal to 0. But then it's going to go down to negative, right? In negative infinity, right? Okay, that's what that's going to look like. And then the domain. So the domain is going to be, remember, x could be anything. So it's going to be right here. So from negative infinity to positive infinity, right? Which happens to also be the range of the other one, remember, because they flipped. So we're just going to write that in. I'm going to do it right now. All right, and then what about the range? Remember, it goes down as low as close to 0, as close to 0 as it can. It just can't reach 0. Remember the electric fence, I'm not touching you, like that thing, right? So it's going to be from 0 to positive infinity. So from 0 on up. And same thing with the domain of the inverse, right, of the log is going to go from 0. So it can't touch 0. It'll go anywhere to the right. It's to positive infinity. There we go. And intercepts, we just talked about them right now. That's, oops. So this one has a y-intercept. Where does it have a y? Is at 0, 1. And this one has an x-intercept at 1, 0. Very much related. Asymptotes. Do you remember where the asymptotes are? Oh, we should make them green. Okay, so asymptotes, remember for this one, it's going to be right here on the x-axis, which means that it's y, because this is where what y is equal to 0 every single time, never without fail, right? So this is y equals 0. And this one right here is where x equals 0, because x is always 0 on the y-axis. So x equals 0. And what about your end behavior? Ooh, the best part. So end behavior. So as x approaches, right? What is x approaching? Negative infinity. They're going more and more to the left. What are we doing? As x approaches negative infinity, f of x approaches 0 because it gets closer and closer to 0, right? So the more left we go, the more towards 0 y is going to go, right? So that's going to be, it's going to approach infinity and approach 0, I meant, sorry. And x, as x approaches positive infinity, what does f of x approach? So as more to the right we go, what's going on? Graph is going, whoop. So it's going all the way up to positive infinity. All right, and we'll try that for this one right here for the logs. So as x approaches, okay, normally we say negative infinity, right? But remember, we literally can't go negative. It never goes negative, right? So as how far left can we go? 0. It's as x approaches 0, right? So as x approaches 0, what is now this is g of x, so we're going to use g of x. G of x is going to approach what? G of x is going to approach negative infinity. And other way, as x approaches positive infinity, so the more right we go, what does g of x do? It approaches positive infinity as well. And remember the flip-flop, right? So this What was now X is now Y. And what was now Y is now X. Flip-flop. And obviously same thing with here, but you just can't tell because they're literally the same thing. They're both just like infinities, right? So yeah, it's the same thing. So you can't really tell for those, but they did flip-flop, just saying. All right, so that's the end of it. Don't forget to do your homework, do the exit ticket and self-reflection. Yes, if you can do the self-reflection, put that in the chat, please. And everybody will know what to do. Thank you. Have a good day. Bye. I'll see you guys later.